Hey, hi guys. Today we are part of the Team 6, and our project is face reconstruction from a particle embedding. And this is purely explaining how, if somebody is able to take some portion of the embedding of your face, how a hacker can really reuse it and build the entire face and guess which person is really is or she is. So, along with me, I have my fellow colleagues. Sridhar is there, and then Avesh is here. So we all three, working on this project, and this project we're gonna give few of the I'll say, the practical output where you can think about how in today's modern world the technology we are using for the biometric authentications or the face recognition, what are the security flaw in on those technologies. So to start with, we have taken it. Uh, so if you look at this slide, it talks about how the modern authentication really works. So if you look at the phone, the iPhone or the Android phone that you have, generally we use our face to unlock the phone, right? What this algorithm behind phone working is doing, it taking your face as in pixels, or I'll say it convert your face into different dimension, and the number somewhere you call the 512 numbers. Okay, that's called the face embedding. So basically converting a picture into a dimension, that's what the embedding is all about. Now, what we think, the moment this code is being stored or converted by your phone algorithm, we think it's the safest thing to reside because you're not sharing the data, or you're not sharing the actual picture of yourself, right? But think about it, if any hacker is able to just consume the 30% code, okay, or 30% embedding of your picture, do you think it still be able to convert into the real image of yourself? The answer is yes. That's really happening, and that's where you're seeing a lot of identity theft is happening across the world. So how do we do that? Okay, what is the next step? So we choose a data set of MFR2 data set, which was containing 269 images, and then we had around 50 plus images of the celebrities. So we use a model where these picture was having some of the noise, like some of the picture was having a mask, right? Some of the picture was not into the right direction. We clean our data set using one model, and then that model detected what are the noise in the picture, how many picture have contained the mask, how many pictures are not aligned with the right angle. So that model really clean up all that junk data and then gave us the clean images. And then we converted those clean images into the embedding code into a different dimension. And you can say the 512 number of those picture. And then we had exactly the face embedding for those clean picture. Then we try to start gradually with the 10% embedding. We just deleted the 10% of the embedding on the face of the clean data, and we say whether we are able to replicate the exact image or not, and gradually increase to 30% to 50%. So when we were doing this experimental, the result was really shocking. Okay, all three percentage, whether it's 10%, 30, or the 50%, somehow the algorithm was able to detect which is the real person face are. Okay, and when we're doing this training, the shocking result again came up. Even the famous celebrities, where you are just getting a partial of their images, still you'll be able to guess the image of that, the celebrity, because the model itself is trained with multiple of such images to guess the right person, face recognition, right? So let's start with the data set and the cleaning. So as I explained earlier, there was around 269 raw images that has been poured. And out of that, we used the Connext AI, which actually clean the data, remove the fuzz, remove any noise, and then give us the clean picture with the right dimension. Now, with this, the score that we use, or you can say the confidence score of the model was 85%, which means there was still few picture which was having few of the noise on it, but that was enough for our next model to process the data and finding the perfect match of it. So 71 perfect full face picture, and then we resize into 128 into 128 dimension or the pixel just to ensure that we are processing it on the I'll say the CPU processor or a lower grade GPU processor, just to avoid the the resource crunches. And we split 49 for the training and 22 for the testing, and that's how the data set was really divided into different parts. Once the dataset is being clean, we process this to the Inception ResNet V1, which is the second model we have chosen, and this model is trained on the photos. Okay, this model has containing a lot of training photos as part of the the reconstruction or the trainings of the same model. Now, when we just try to process the 10% of your face embedding via this model has given us different metrics, which my fellow colleague will gonna, explain. So when we extract 30%, 50%, we were able to see the results was around 94% similarity. Okay. And when the person was no matching with the face embedding, the similarity was around 12 to 12% to 13%. So that conclude that this model was able to recognize a person and able to work on the facial embedding of a person. So for the next set of slide, I'm gonna hand it over to Sridhar. Sridhar, why can't you take over and tell the next processing part of the model?
Yeah, sure, Rohit. Thank you. So till now, so Rohit was explaining about so the data set which we chose, the MFR2 data set, so which has celebrities and how we has used different model to identify the real celebrity faces and use it for our training. So now, once we have the full faces which we chose, so now we have intentionally removed the dimensions to make our so to build an neural network, so which can basically read this dimensions removed, data removed uh, photos, and try to understand it and then try to reconstruct the face from this partial embeddings. So for that reason, so what we did is, so we intentionally removed 10%, 30%, and 50% of different stages of leakage from the embeddings. So these embeddings are planned embeddings, and so we call it as ablations. So this 10% of ablation is done particularly on zeros. So we have targeted random zeros, and we have removed nodes to simulate this 10% leakage, and also 30% leakage, and also 50% leakage. So there are two ways to do this ablation. So one is this random zero selection, and the other way is noisy data selection. When we identified that no our once we trained our neural network with this, so what we have identified is, so instead of removing the random zeros ablation, so when we had targeted ablation, choosing the proper noisy data and removing the zeros, so we had better results that we are going to explain the result side. So this is a an controlled ablation which we have created for the training the model. So next I'm going to explain the architecture, so how we have created our model. So as you can see from this diagram, so first we chose the photos, the unfiltered masks, the original face of the celebrities in different scenarios or different settings. So we filtered those masks, and we had a clean data set of 71 photos, and we turned that 71 photos into 512 dimension vector embeddings. And then we have created a simulation or controlled simulation of leakage with ablations. And then we used an autocoder, basically a neural network, so which we have trained to with these leakage photos with different settings to reconstruct the original photo. So we have gone through different autocoders for this, and finally we chose so we chose the VGG phase 2 autoencoder. So because it has a great means it's already proven in the industry. So it's an production grade autoencoder which has no but very good results of 94% of results, exact results. So then once we started training with this model with the 71 photos, so next we trained this model on these broken images to guess the faces, and we got very fast. So when we started training, so I put an LE exit. So what happened is when it is training, so uh, the model was able to, we can see that the training loss is decreasing. So we can, as you see from the graph itself, so 0.29 to 0.26, the efficiency is increasing, and the model opted out from 16 rounds of training itself. And so it makes us clear that the model is able to uh, train and no clear reconstruct the images very clearly to the and match it to the original uh, original celebrity face within no time. So it has only taken 16 rounds of training. Yeah, so the next slides, my teammate Navesh is going to continue.
Thank you, Rohit. Thank you, Sridhar. Right, we have seen that Rohit has explained about the MFR dataset, and we have seen what Sridhar has talked about the architecture diagram and as well as the training part. Now I'm going through the result one. When we randomly delete the 30% of the 512 number embedding, that is 153 numbers gone. Our attack can reconstruct a face that achieves an average cosine similarity of 0.62 with the original photo. So to put that in perspective, most commercial face recognition systems match at a threshold around 0.5 or 0.55. In fact, when we feed these reconstructed faces back into original Inception ResNet V1 recognizer, the identity match rate is 100%. Every single time the system says, yep, that's the same person. Even at 50% missing data, we still recognize the faces, but it's a bit blurry type. We will see that in the next slide to show us the example. Now here the proof, our proof. Left side, we can say that that is a real celebrity photo, and the right one, it is an embedded photo, auto-encoder photo. So that's not a vague, blurry face. That's clear a person. You can recognize the jawline, the eyes, the expression. At 30% missing, the reconstructions are shockingly good. Even at 50% missing, it's blurry. But if you know the dataset, you can still exactly tell who he is. We also overlaid heat maps of pixel-wise error. The red light area, the red areas show where the reconstruction is washed. Interesting, most of the error is the background, air, or lighting, not the core identity features. Next slide, we'll talk about the defensive results and other attack. We are just trying to break things. We are also wanted to see if we could make it harder. We noticed that some dimensions in the 512 number code are very noisy. They change a lot because of lighting, angle, or background. So instead of deleting random numbers, we tried deleting the noisiest ones first, thinking that that would perfect identity better. Actually, the opposite happened, shockingly. Prioritizing noisy dimensions made the attacker easier. So we flipped it. What if the system deliberately hides or protects the noisiest dimensions first? The simple idea. Basically, reordering which parts leak made the attack roughly 8% harder across the board. It's not a full fix, but it shows that small changes in how embeddings are stored or transmitted can buy meaningful protection. Next slide, I'll take over the conclusion part. So here's the big takeaway, and it's kind of a terrifying part for us. The 512 number secret code that your phone, your bank, and off the internet uses the recognition are not secret at all. If an attacker gets just 70% of your embedding, which could happen through a partial database leak, side channel attack, or even purely encrypted transmission. They can reconstruct a photo that will fool almost any face recognition system. We showed this on real state of art embeddings with a pretty straightforward encoder. And our first defensive idea already gives an 8% improvement, which means there's low hanging fruit to make this better. But right now in 2025, most systems are still wide open. So the bottom line here is these embeddings were sold to us it as safe, irreversible ashes of your faces. They are not. They are more like a compressed JPG that any decent AI can uncompress. We need to fix this before partial embeddings leak become the next big biometric scandal. So thank you from our side. Happy to take any questions that you keep us.